This is the single most important experiment in all of physics. It was the experiment that gave birth to quantum mechanics. And this is the second most crucial experiment, forming the foundation of the theory of relativity. But guess what? These two experiments are essentially the same thing. Both of the experiments can be simplified down to this, the simple case of two spherical wave sources, where in any point in space you can measure the sum of the two waves, because of something called the superposition principle. When you're perfectly at the same distance from both, the waves reach you at the exact same moment, syncing up in a harmonious pattern. However, shift just a tad closer to one and farther from the other, suddenly the waves don't align anymore, they cancel each other out. With a change of just half a wavelength in position, these waves can either combine to create a more pronounced wave or negate each other. These intriguing variations occur when the distances shift by half a wavelength. And this dance between alignment and misalignment is what we call constructive and destructive interference. But how do we calculate the distance difference? Now imagine we've got these two wave sources. No matter where you are, we'll call the distances to the sources D1 and D2. But what we're really after is the difference between D1 and D2, as we already know the values that will let us see some cool interference patterns. To derive these distances, we only need to look at the right triangle from the source to the point. Now look closely. The height of the triangle is just the y-coordinate, and the base is just the source distance plus your x-coordinate. And now we have an expression for d1 squared. For the other distance, we can do the same, but now the base is the difference between the source distance minus the x-coordinate. Finally, we have an expression for d1 and d2. We can take the square of both sides and substitute in our original equation, and we get this really big but beautiful equation that works for any pair of x and y coordinates. Now, we've identified the phase shift values for both constructive and destructive interference, and we're also aware of how it relates to the x and y coordinates. By plotting the values of delta D, we can pinpoint the lines of constructive and destructive interference. When we input 0 into the equation, it yields a straight line. This is intuitive. As you traverse the central line, both of the waves maintain an equal distance to you. Next, plotting the subsequent values reveals hyperbolic curves. Observe the center. Measuring across that region, the Young's interferometer interference patterns emerge. But there's more to explore. In 3 dimensions, given the x-axis as our symmetry axis, these hyperbolas can be revolved around it, resulting in a unique shape. Rotate and examine these circular hyperbolas, and there it is, the interference patterns of the Michelson interferometer come into view. And that's how, in essence, both interferometers can be simplified to taking measurements across a plane in this ideal scenario.